I'm about to start the first metered discharge test. So this battery is the one I just drained out with the heat. This one's down to about 20%. This is a nearly full battery. So I'm using the iCharger to drain this battery down back into this battery. It is quite cold out. You're not supposed to charge a battery that's below 32 degrees, below freezing. This one I kept in the house for a couple days, so this is a warm battery that's about to be drained. Another good point of reference here I have is this bucket of water in the garage has been sitting for a couple days and there's no ice at all, so we're not below freezing. So good to charge up this one. I've got a BMS on the full pack running into the iCharger. It's measuring all the individual voltages. I'm going to run a test that runs those voltages down to 3.5 volts, which is about 20%, and cuts the test. And then I have my other BMS here, my not smart BMS here, just to cut if any overcharging happens on this one, if this happens to give out more energy than this one can take in. So this would cut the test, and it would sense that it's not able to output anything. It would cut the test here also. So the first thing I do is, this is considered the input or the supply, even though I'm discharging into it. So I plug my connector into the upper input part here for the iCharger. And then this is a part that a lot of people skip and don't talk about. So this little wheel here, if I hold down on it for a second, it'll take me to the system menu. And this is where in the charger setup, I want to come to input and power limit. I'm going to click that. And then all of these stock are set to the same. So I've already edited this one. But what you do is you need to set up what your input is. So if I click this, so since I'm discharging into this battery, I can also discharge out of it. So I'm setting a low voltage limit, max current, high voltage limit to make sure no damage happens. Then also I need to make sure that regenerative enable is checked. And then I'll save, which I've already saved, and I'll exit. But then you'll see your stats are there. So then I'll exit out of here. So now that it's preset, I took the plug out again. Now I'm going to put it back in. And in the first second, I need to click this button right away and click that profile I just created and select it. All right, so I clicked and held that to enter into here. That is super important. I wasted hours figuring out why I couldn't get this to work. So hopefully this helps showing all of that. This helps people get to this right away and not waste hours reading around and figuring why they can't get things to work. I was getting all sorts of errors saying this battery's voltage was too low or wouldn't support regen. So now the battery I'm testing, I plugged its connector into the input here along with the balance leads. So this is my full battery, 24.6, and then each individual cell voltage. And then right down here, this is my battery I'm throwing charge into regeneratively, is at 21.5. So this is at about 100%, this is about 20. Now I'm going to select a program I've created. So I hit this button once. Then I've already created and saved it as Tesla. I'm not going to show how to do this. This is a lot easier and more intuitive on how to create these profiles. Makes more sense and easier to set up than that initial source power charge thing that I showed in the beginning. So I'm going to select it. Let me go to the discharge. I'm discharging down to 3 volts, regenerative. I'm going to select it. Are you sure you want to run? Yes. Now it's asking me, am I sure that I want to do a regen discharge? I'm going to say yes. So here it's already running at 30 amps. It's taking the voltage of the cells down very low. I think this cell is dead. I think this module's dead. I'm already down to hardly anything. It's a lot of voltage sag for just 30 amps. After 21 minutes, they're all holding at about 3.6 volts, 0.1 volts above the cutoff, and it's been about 10.7 amp hours. So it's quite strange. There was a huge voltage sag right away, and now it seems to be outputting the power. Either way, I don't think I want to put this in the car because that's a ton of voltage drop, and that could... I mean, I'm going to set the car BMS settings to detect a min voltage, and if this is hitting a min voltage really quick, it's going to render the range pretty useless. Now this is strange. After another 20 minutes, it's gained charge. They're up to like 3.65. So I have no idea what's going on here. Over an hour and a half in, it's put out 50 amp hours so far. It's getting late and starting to get cold. I'm going to stop the test for now because I don't want to charge this below freezing. And I'll resume again tomorrow. It's the next day. I restarted the test. So far it's about an hour in. 25 amp hours plus the 50 from yesterday. We're at 75. And the amps have been dropping from 30 down to 16 slowly. Well, almost all cells are at 3.5 volts. So about 10 minutes later, the test stopped. 28 amp hours plus 50, 78 amp hours. Then all the cells bounced back up to 3.7 volts. So there's some serious voltage sag going on in this pack, where maybe it holds more energy than that, but either way, that's going to sag a ton in the car, so I don't think I want to use this cell. So if the cells are at 3.7 volts, that's halfway through the discharge. Even so, I've got 75 amp hours. If I only used half, that's 150. This is supposed to hold 230, so this module still is pretty degraded and not performing well. And that's exactly why I'm running this test, so I wouldn't run into problems after I installed it in the car and have to find more modules later. This is the battery that had some arc marks, so at some point this shorted, so that's probably why this is damaged. So I figured out what was going on. This is the data sheet for the Panasonic cells within the Tesla modules. And then this is the discharge curve at various temperatures. And so I've been testing at about 0C, this second from the bottom line. You can see right away the voltage drops almost all the way to 3.5. And I can actually see the curve picking back uphill, gaining voltage, and that's exactly what I was seeing during my test. And so, also, I should be discharging down lower. I had it at about 3.3 volts before. And if I run the 3.3 volts across for the 0 degrees, only getting about halfway, 1500 of the 3000 down all the way to 2.5. So really, I need to run my tests down lower to about 2.8 volts to get deeper in this curve to get a more accurate estimate of how much energy is in my pack. So for all the following tests, I will discharge down to 2.8 volts, which will get me to about 2700 milliamp hours out of the 29 expected, and I can extrapolate there accordingly. So now the module that I was just charging only got charged up about halfway, so I'm going to discharge it down again to about 3.5 volts so that I can discharge this fully charged next module into it. This module that I just tested, I'm going to take the cell tap off of it and put it on this next one. Got the next cell lined up. My empty battery is at 18.8 volts, a little above 3 volts each cell. My full battery is at 25 volts, almost fully charged. I edited the program this time that I'm going to go down to 2.8 volts to get deeper in that discharge curve rather than 3.5. So let's see how it goes. So this cell is just as cold as the last one, but the voltage only dropped to 3.8 right away. So I still do have some concerns with that last cell, since it's not consistent with this one. So something else I just found out is the thermistor plugs in to the right connector on these boards. And based off of the ohms on those thermistor, I know the temperature of the board, so I can be sure that I'm not charging below freezing. I think it's right at about 27 kilo ohms. And greater is when it's below freezing. So here I'm good on this thermistor, and then there's a second one I can check too. Also below 27 kilo ohms. This started at about 26. So as soon as you start charging the pack, it does warm itself up a little bit, and the same goes for discharge. There's some losses and it ends up heating itself, which is kind of beneficial. This is the second module being tested. This is the second half of the test. It was at 112 amp hours. Now we're at 72. It's roughly 190 total. And now also you can see the battery I'm charging into is registering that it's taken in 160 amp hours. So there's some losses, 180 to 160. That's also a measure that the charged battery is taking at least 160, so that's a good sign. The test just finished for this battery. The cells dropped to 2.8 volts, then bounced back up to 2.95 once it was done. About 85 amp hours in this one, plus 112 for part 1 of the test. So that means 196 amp hours at about 0 degrees Celsius to drop these cells down to 2.8 volts at 30 amps. And something that sucks is I just had this ribbon cable snap here. So I gotta figure out if I can solder onto this ribbon now. This really sucks. To repair this broken ribbon cable connector, first thing I did was I took sandpaper and sanded off the top layer of plastic till I could see shiny copper. Then I got 3 pieces of 24 gauge wire, soldered them on there, and covered it up with epoxy so that a drop of water can't have it short. Then, with this chunk of sandpaper, I scratched a good spot on each lead where I can solder and where they're not too close together because it's pretty easy to short. If I did them all 3 here on the end, it's pretty likely that they would short once I went to go finally connect the wires to the solder. So all these you can see scratched onto bare copper, and now I can solder a 24 gauge wire onto there. So now I've finished. You can see I soldered each wire where I scratched the copper clean. Then I put a dab of epoxy over. Now this section here was a little tight and a little worrisome that you could possibly short while soldering. So if I were to do it again, I'd suggest this 5 line, which is the middle wire. Maybe run it all the way back here so you're nowhere near the left wire. Now I've also got way more flex than I had before with this, so I think this is a better fix overall. Now I'll just put a strip of Kapton over. Just started the next test, less than a minute in, and the voltages dropped down from like 4.2 to 3.85. It's even colder this morning, so this one's doing quite well. I haven't tested either of these modules yet because they have a different connector style rather than these blue connectors. For this module that has the single style white connector, I actually bought the mating connector that's supposed to go on a board, and I just soldered individual wires to match up with the pins for the voltages. Ran that into the terminal block, had them in parallel with the cell tap reader for the iCharger. I could have just bought a Rev 2 board for this and not done this with the connector, but this connector was $1 and then it took about 15 minutes of soldering and crimping, so I went this route to save about 20 bucks or so. This one's another story. I can't detach the board and get at the individual cells, so I think I will do this with the ESP32 controller, which I will be hooking up soon. So now I'm testing this final unit where I can't remove the BMS board. So I took this as a good time to test out my ESP32 EVTV controller. So I have a wiring harness that plugs into the controller. This is a shorting plug. You can do a whole bunch of these in series, and it communicates over CAN and gives the cell data to this controller. It's got a positive and a negative line. If it senses anything wrong with the cells or the temperature, thermistors are also sent through this line, temperature, it will cut the negative or the positive line. Now I got very delayed on this because I bought this from someone who said he never set it up before, but when I tried to work it the first time, I would press this on button and the red contactor light would come on right away. It's not supposed to do that. You're supposed to turn it on, 5 seconds red goes on, 5 seconds green goes on. So it turns out it was because there was a bad contactor in here, which makes sense because I knew I was inputting voltage, and then I was measuring the output voltage and getting nothing. So something was busted with the contactor on the negative line, so I wasn't getting any current through. This is the inside of the box. I had to take out the bad contactor, which I have here, and put in a new one. So pretty simple swap out, but this did cost $200, so it wasn't cheap. This thing is really nice. It also has a heat enable for coolant. If you get at a certain temperature too high, it'll start your coolant pump and start running coolant through the coolant loops, which is something I might add later. It has a charge enable, so it can communicate with your charger, turn on and turn off. It has a printer cable port to read data off of it to a display. So just like before, these are the input leads, and then I'm going to output into the hot tub and read the data off of here to see how much energy is consumed. And so over here I have a display. Right now this controller is communicating to this display wirelessly through this mini router. There's no cable connecting these two right now. So my plan is to put this in the dash of my car, communicate wirelessly via that, so I can always see what's going on. And so you can see it gives me a percentage, how much current I'm currently drawing, voltage of the module, temperature, and all the cells. It's showing 6 cell levels right now and how much power I've used over time. So this is super helpful. It's also, I can configure all of my voltage settings that I want, my temperature limits and whatnot. So this thing is really cool. And so now I'm reading the live readout that's on CoolTerm on here. I just connected the heaters to the input and output, and it is reading 588 watts. So I had an earlier video where I was assuming 800 watts. That was a bad assumption. This is a much more accurate and better measure. And then it's counting cumulative amp hours for me here. And since it's a little warmer, it's telling me my average temp of the cells is 9C right now. So I can match it up to the 10C discharge curve for expected capacity. My low voltage cut off at 2.8 volts, so this is going to automatically run the test for me until it hits 2.8 volts. It's also calculating the state of charge. So it's really cool to see all this up and running and kind of how it's going to be working all together in the car. I'm ending the test for the night now. It's at about 73 amp hours and like 66% state of charge. I'll resume tomorrow. So I hit the low voltage cutoff, the contactor's cut off, and it's at 193 amp hours. This curve is from EVTV for estimating the state of charge based on static voltage. This is for 2S, so since I'm testing one module at a time, I gotta multiply by static voltage by 2. So for example, if I started a test at 24 volts with one of my modules, times it by 2 would be 48. Brings me to this point here, which I run upwards to the green line and then across. I can see that's about 83% state of charge. And all my tests ended at 2.8 volts per cell, but they bounced back up a little bit. So even if they bounce back up to 3 volts per cell, times 6 is 18, but since there's 2 here, it'd be 36. All my tests were ending at 36 volts, which if I go out to 36 volts and run it down, that's 0 state of charge. So all my tests were ending at essentially 0 state of charge. So here are the final results. For every module number, I took the voltage they started at and the voltage they ended at. I used this curve to estimate the state of charge. And so for example, this module number 1, 197 amp hours during the test, I divided by 0.99 for 199 amp hours for 100% discharge. Similarly for this one that started at a lower charge, so I did 140 amp hours during the test divided by its 0.86. So when discharging down to 2.8 volts, there's 74 cells that at 0C Should each have about 2.7 amp hours, according to this curve. So I multiply that out, and it's an expected 200 amp hours. If I were to discharge down to 2.5 volts, there's a little more energy left, but that's unrealistic because when drawing heavy currents at those low voltages, the voltage is going to drop, and you'll hit 2.5 almost immediately after 2.8. So this last 15 amp hours is really only usable at very low discharges. So then I took my projected full and divided by the expected amp hours to get state of health. 186 divided by 293. For my last module, it was at 10C, so each cell is expected to get 2.9 amp hours. You can see it's a little further to the right. So the expected there is 215 amp hours, so I took my 197 divided by 215 to get 92. So this is the final number that's important, is the state of health. So I've got 1, 2, 3 modules that are all at essentially 100%, which is awesome. I was not expecting that for how long these were sitting at a high state of charge. This module is the worst at 82%, and then these two are at about 93. So what this means is I'm going to keep an eye on this module. This will likely be the one that hits a low voltage first before all the others. So my range will be limited by this module. This will empty first. So realistically, my whole pack is going to have about 163 amp hours of range, even though these won't be using the bottom 40 at all. I will also put the ones that are not at 100% higher up in their respective packs, so if they start getting bad and I need to replace them, I don't need to dig to the bottom and they're right there on the top. And the last thing to mention was I took some internal resistance measurements, and it seems to correlate with the state of health. So this had 0.7 milliohms, 99%. 1 milliohm, it dropped down to 82. 0.8 milliohms, it dropped down to 93. So maybe a quick way to check this in the future would just be to look at the internal resistance of the packs. And finally, most of the time I'm driving, I'm going to be at the 25C ambient temperature, which moves my projected cell capacity all the way to 3.2 amp hours. So at 25C, my 74 cells times 3.2 times the 0.82 that I have from this cell up here gives me 194 projected amp hours. So that's what I'm going to use for the EVTV BMS controller as it tracks power loss throughout the discharge, is the 194 to calculate my state of charge. That's my expected output at most of my driving temperatures. And I can adjust this value within the controller over time. So in the winter, I can adjust it down to 200 times 0.82, so down to more like 170. I can adjust it as the seasons go along, so I have a more accurate projection. Overall, this was a lot of work to test all these modules, but I'm glad I did it because I know where my pack is at and I know what to expect, and I have realistic expectations and know what modules might be my limiting modules. And next, now all my modules are all over the place in terms of voltage. Some are low, some are high, some are medium. Now I have to level all those out before I can put them in the boxes.